We can do that algebraically with substitution or elimination, or graphically by graphing both lines and seeing where the point of intersection is. So let's do graphing first. In order to graph both of these lines, it's easiest if we rearrange them into y equals mx plus b form. So I'm going to isolate y in both of these equations. Let me start with the x minus y equals 5 equation. Let me isolate y. It's the easiest if I isolate it to the right.
Granger knows that if you're a maintenance supervisor in a manufacturing facility and your machinery isn't working right, you need to understand what's wrong as soon as possible. So when a conveyor motor falters, Granger offers diagnostic tools, calibration, and technology to help you identify and fix the problem. With Granger, you can be confident you have everything you need to keep your facility running smoothly. Call 1-800-GRANGER, click Granger.com, or just stop by. Granger, for the ones who get it done.
And now you can see it's in y equals mx plus b form, where m is the slope, and in this case, our m value is 1, and b is our y-intercept, and in this case, our b value is negative 5. So we can use that slope and y-intercept to graph the line. We would plot the y-intercept as negative 5, and then use the slope of 1. Remember, slope is rise over run, so you may want to rewrite that whole number 1 as a fraction, 1 over 1. So rise 1, run 1, plot a point, and keep plotting points until you fill the grid. And then we'll connect them with a straight line, and we'll go through the same process for the other line. Let me isolate y. I'll just move the 3x term to the right, it becomes negative 3x. So it's clear that for this one, the slope is negative 3, and the y-intercept is 3. Plot the y-intercept, and then use the slope. And remember, any whole number is over 1, so you can think of this negative 3 as negative 3 over 1. So rise negative 3, run 1. That means down 3, right 1. And keep plotting points until you fill your grid. Connect them with a straight line, and then just find where these lines intersect, and that's the solution to a system. These lines intersect right at that point right there, the point 2, negative 3. That's our point of intersection. So we could say the solution is, you could write it one of two ways. You could write it as point 2, negative 3. Or you could write what x and y are equal to. You could write x equals 2, y equals negative 3. Either would be acceptable ways of writing the final answer. Let's solve that same system using elimination and substitution. Elimination first. So in doing elimination, you want the equations in the format x plus y equals a constant, which both equations are already in that format. Now our goal here is to eliminate a variable, and the way we do that is by making the coefficients of either the x's or the y's have the same absolute value. Now in this example, the coefficients of the y's already have the same absolute value. The coefficient of y in the first equation is negative 1, and the coefficient of y in the second equation is positive 1. Those have the same absolute value, but because they're opposite signs, adding the equations will make them eliminate. If they were the same sign, subtracting them would make them eliminate. But in this case, since they're the same absolute value but opposite signs, if we add these two equations together, the y's will eliminate. Why? Let's add the equations, and when we add the equations, we make sure we collect the like terms. That's why we have them lined up. X plus 3x is 4x. Negative y plus y is 0. That they eliminate, which is what we want. And 5 plus 3 is 8. We have 4x equals 8. Divide both sides by 4. We get x equals 2. So we have the value of x that make both equations the same. But what's the value of y? We now need to sub x equals 2 into either of the original equations. It doesn't matter which one you plug it into, because that's the value of x. It makes both equations have the same value of y. I'll choose the first one. Let's use it. So sub 2 into x. 2 minus y equals 5. I'll isolate y, move the negative y to the right, move the 5 to the left. That 2 minus 5 equals y. Negative 3 equals y. So notice, my solution, x equals 2, y equals negative 3. That's the same thing we got by solving it graphically. Let's try it again, but using substitution. Now when doing substitution, I often like to line them up side by side like this. I'll still number the equations, equation 1 and equation 2. When doing substitution, what you want to do is isolate one of the variables in either of the equations. It doesn't matter. I think in equation 1, the variable x looks like it would be easy to isolate since it already has a coefficient of 1. So I'll pick this x to be the variable that I'm going to isolate. So I'll move this negative y to the right, and that's a positive. So that's x equals 5 plus y. now what you do is you take what variable you isolated from. So it says x equals 5 plus y. You take that and plug it into the other equation for x, because we know x is equal to 5 plus y. So now in the other equation, I have 3 times 5 plus y equals 3. Now we have an equation with only one variable. This equation only has the variable y. We could solve this for y. Let me distribute the 3 into the brackets. Collect my like terms. 15 plus 4y equals 3. Now I want to isolate the y, so I'll move the 15 over. 4y equals 3 minus 15, which is negative 12. Divide both sides by 4. Y equals negative 3. I now need to solve for the other variable. What we have to do is take that answer and plug it back into either of the original equations. It's always easiest if you sub it back into the rearranged version we have, because x is isolated. So you just take this answer for y we got, plug it back in for y there, and then we get our answer for x. So it has x equals 5 plus y, which we know is negative 3. So I have x equals 5 plus negative 3, that's 5 minus 3, which is 2. So I got x equals 2. Y equals negative 3. Same answer again, just a different method. Example 2, solve the following linear system using elimination. So this one's much harder than the first one we did. For this one, we have 2 equations again, and both equations are already in the proper format, with x and y on one side of the equation and the constant on the other side. But we want to eliminate variables by adding or subtracting the equations, and to do that, the coefficients have to have the same absolute value. And notice the x's have different coefficients and the y's have different coefficients. So what we're going to have to do is multiply one or both of the equations by a constant to make the coefficients have the same absolute value. What sticks out to me is we can make the x's have a coefficient of 20, or we can make the y's have a coefficient of 12 and negative 12. Let's make the x's both have a coefficient of 20. So I would have to multiply equation 1 by 5. So I'm going to do 5 times equation 1.
Daisy, Mark Jacobs.
The 2026 Chevy Equinox is ready for your daily drives, weekend getaways, and everything in between. Plenty of cargo space, plus a touchscreen that keeps all your tech right in one. It's more than an SUV. It's your Equinox. Chevrolet. Together, let's drive.
And that would give me, so 5 times 4x is 20x, 5 times 3y is 15y, and 5 times 13 is 65. Make sure you multiply every term by the constant. And for the second equation, for the x to have a coefficient of 20, that's multiplied by 4. So 4 times equation 2. And that would give me 20x. 4 times negative 4y is negative 16y. And 4 times negative 7 is negative 28. Now what I'm going to do is I'm going to figure out if I add or subtract these to eliminate the variable. The x's have the exact same coefficient with the exact same sign. They're both positive 20. So subtracting will eliminate the variable x. So let's subtract all the like terms. 20x minus 20x is 0x, so that's gone. It eliminates. 15y minus negative 16y is 31y. And 65 minus negative 28 is 93. Divide both sides by 31, and we get y equals 3. Now we need to sub y equals 3 into either original equation. So I'll just sub it into equation 1. Let's sub our answer for y into that equation. So 3 times 3 equals 13. And then we just solve this for x. So 4x plus 9 equals 13. Subtract the 9 to the other side. I get 4x equals 4. Therefore, x must equal 1. So my solution to this linear system is x equals 1, y equals 3. If we were to graph both lines, they would intersect at the point 1, 3. Example 3. Here's an application of solving linear systems. A sports shop sells Adidas shoes for $82 a pair and Air Jensen basketball shoes for $95 a pair. One day the shop sells a combined 75 pairs of shoes, totaling $6,200. How many pairs of each shoe are sold? Now for these types of questions, you're always going to want to solve for two variables. In order to solve for two variables, you must be able to make two equations that involve those two variables. So I always like to start by figuring, okay, what variables am I going to be trying to solve for? So it wants to know how many pairs of each shoe are sold. So we're trying to figure out, okay, how many Adidas shoes were sold and how many Air Jensen shoes were sold. Those are my variables. I'll say x equals number of Adidas and y equals number of Air Jensen. in order to figure out what the value of these variables are, I must be able to make two equations that involve these two variables. Well, I know they sold a combined 75 pairs of shoes. So my first equation, x plus y, equals 7.